Okay, let's continue the deep RI here. So deep RI is the process is called the Bosch process as well because this was developed at Bosch's, the company in Germany. Um, as you see in the name of the process, this is the one of the RI process, but this is for deep etching using RI, right? That's kind of a deep RI, right? Okay, but when we use this machine, actually, particularly, you can buy like the machine called ICP, okay, ICP or ECR. So this kind of a machine is you need for deep post process, okay. So the key features of this process is you need a high density plasma, and then you need the low bias voltage for high selectivity with respect to masking layer of the photoresist. And then rapid switching between the etch and deposition cycle to obtain the passivation of vertical sidewall. For example, over here, let's say you have put some uh, uh, um, deposition of polymer here, and then you put the second layer will be you make etch over here, okay, and then you put the other like well, okay. So what new step is you have a tapeworm like polymer deposited, and then you have second deposition is uh, you put the polymer tapeworm like a polymer etching done, and then you do silicone etching, right? So the key over here is you need to keep you have keep very good protection of the sidewall. Okay, that's the key. Okay, and then while you keep etching down the silicone layer here. Okay, so let's talk about this a little bit more. So this is like a cyclic process. You put the tapeworm-like polymer deposition first, and then you etch it. Etch number A, and then etch number B is the right. You have a so you have put the so you have a kind of double protection, right? You have put double protection, and then you etch the uh, uh, etch A for the polymer, and then you have silicon etch second, and then what is next step? You apply this green layer again, and then protect the sidewall, and then you etch the silicon again. That's kind of you repeat this cycle over and over again. So for each cycle, you can reach like a 0.5 micron. Okay, so when you want to guess through, almost to guess through the 500 micron, and then you have like 1,000 cycles to get to reach the other side of the wafer. Okay, so that's they looks how they looks like. You see this very high speculation structure like GC application. Gas chromatic application, you have you see the dimension over here from here to here is 250 micron. So so the width of the wall probably between somewhere 50 to 100 micron, but the depth maybe let's say about 8 or 9 times larger than the width of the wall, right? So that's the higher aspect ratio. But if you take a looking closely about the sidewall, you see these like steps of a push process, right? So it's coming down, those 3 cycles until you get the certain depths that you want to have. Okay, so that's those 3 steps that keep cycling. That's so basically that's automatically scheduled in the recipe of the ICP machine that to keep cutting down the silicon wafers through the keep protection of the side wall. Okay. Again, the key in this process is the how you keep protect the side wall. Otherwise, you have etched the side wall, then you're going to lose your pattern. Okay. Okay, or so this is the example of dry etching process, to build the MEMS resonator here. So over here you can put like a deposit mask oxide, okay, and then you have a pattern it, and then you do transfer pattern here. So register, there is a mask oxide, and then you have silicon substrate here. So now you have a silicon substrate, and the silicon dioxide is the masking material, and then you do deep etching here, okay, and then you protect with the PCVD oxide. This is sidewall oxide, and then you etch down the bottom of the oxide, okay, and then you keep etching down the silicon with the CF4 or with mixture of oxygen, okay, and then actually then you kind of isotropic etching done through the SF6, okay, then the last step will be sputter the deposit material with deposit metals, okay. So this is like a released structure, like you have a release structure. This is kind of example. So this is deep dry etching process is used to have like a certain height of the release structure here. Okay. Right. Combination of dry and wet etching process. Like you may be familiar with this shape. This is like a tip of AFM, atomic force microscopy. So this is very sharp tip. You need this sharp tip to kind of scratch the surface with a very fine tip to have a really nanoscale resolution during the like scanning. Okay, so how to make this pretty sharp tip, right? This is the curious, right? And then what happens is, based on, there is a couple of methods is available. This is one of the methods that using the RI and KOH. Basically, you can opening. This is a backside the opening with the KOH. This is silicon vapor, and then you have a silicon dioxide patterned like this, like a steps here, and then you stop the KOH and with like a 300 micron, like a thickness, right? And then what happens is you start RI from the other side, top, right? The other side of top, okay? And then with the post step, right, you can like etch down like 15 micron, while this first step is protection of the layer, and then this is like removed, and then and then you have additional patterning here, and then over here actually you do isotropic etching here, because you need to have like undercut to have sharp tip. Okay, so you keep going down with the isotropic etching, then eventually this side will be removed, and then now at the end you have like a release structure with the sharp tip at the end. Well, this protection layer will be removed at the last step. So okay, so that's why you got this very sharp tip. So the key is here, the undercut. Keep going on until these two sides are going to meet, right? Then this protection layer is actually automatically kind of released, right? Okay, so that's how to make the AFM tip. Right? It was very exciting, like when AFM was introduced, right? And then making the AFM tip is kind of amazing, right? So now still popular in some material science instrument. But that's what we borrow the technology from the MEMS. Okay, well we can applying the same technology to make like an array of very sharp needle, right? For the drug delivery, right? Which is called a micro needle array for transdermal drug delivery, right? I believe this is commercially available now. The big injection, right? for the vaccine injection for the like kids and small baby is really painful. So instead of a big needle, you can have very fine needle that's enough the long that you can pass through your skin thickness and then release the drugs through the many needles at the same time without pain, like a patch style, right? So to make that sharp tip, like, and then you have certain opening behind, right? So you can make like this kind of structure, and then using the isotropic plasma etching, you can make a very sharp tip, right? So that's kind of the way you can have many sharp needles at the same time. Okay, let's move on to deposition technology and then surface micromachining. So this is surface micromachining is a little this is quite unique for MEMS because this is not borrowed from the silicon microfabrication. I mean the surface micromachining, not the deposition. Okay, well, let's start with the doping. For this chapter, this kind of topic, we're going to talk about doping and oxidation first. And then we will talk about the physical vapor deposition, and then the chemical vapor deposition is like a CVD, right? There's two kinds of CVD available. And then we'll talk about the polysilicon surface micromachining, and then we'll talk about issues in the surface micromachining. So, well, this is one of the representatives of a surface micromachine, the MEMS devices. This is accelerometer fabricated, done in analog devices. So those like patterns, like some of them is silicon, and some of them is polysilicon. This is like it's made through this deposition technology. Yeah. Okay. Okay. Well, let's talk about doping. So as you know, the silicon is semiconductor, right? To make the semiconductor, to make the silicon to be like conductive, right? You need a dope. You need a doping, right? So doping is adding tiny amount of special impurity to the silicon crystal, and then dramatically alter its conductivity. Like intrinsic resistivity was like this high, like 2.3 times 10 to the fifth ohm centimeter. But after doping, right, silicon resistivity goes down like a 1 to 10 ohm centimeter. Okay, so that's kind of a magic of silicon with doping. Well, so you have a kind of choice whether it's N-type or P-type. So you can choose the phosphorus for N-type and then the boron as a P-type doping. So in doping, there are two steps, like ion implantation first, and then you can kind of dry in diffusion, right? That's you needed kind of this two step. So in ion implantation, you need to kind of shoot a beam of dopant atom into the vapor under the low temperature vacuum condition, and then under the PR mask, you need a kind of good protection. Well, sometimes you do doping like in whole vapor, but assuming like you have some protected area. Okay, so ion implantation, you need. I have time to visit the variants in Massachusetts. Now they are merged in the applied materials. They are at the time like 2000. Let's see. I was in there sometime in 2006 to 2013. So I would say 2012 or 2011. The before the applied materials actually bought that the company. So so the way they control the beam direction, right? They using the magnetic field. Actually, there is huge magnetic field that should be generated uh, to let the dopant atom actually bombard into the vapor. Um, so that's very exciting, right? Do you need so basically you have a kind of a either productivity ion presentation, right? Depending on like how you kind of design uh, those uh, magnetics in the machine, then whether you can dope the whole vapor at the same time, or you need a kind of partially should be done. So those that kind of technology, like handling those big magnetic field, that's the key in ion plantation technology. Okay, after that, after this shooting is done, and then you need to kind of let the dopant atom to be like infused into the vapor. That's the step called the driving diffusion. So you need high temperature at the time, and then the silicon dioxide mask, you need that, and then this is a low cost and batch process. This is a more comparing ion implantation. This is really a simple batch process, right? You don't need any big machine actually for this process. You need a furnace, right? You need this temperature, so you need a furnace. Okay, oxidation. So thermal oxidation, this is the important step to making the silicon dioxide on top of the silicon. This is like you create the dielectric material on silicon vapor. Okay, so oxidation, silicon readily dioxide even at room temperature, right? Right. That's why you need cleaning or remove the thin oxygen layer before you're using the silicon. And from the native oxide is about 20 angstrom. Okay. Um, but I mean, for high temperature, basically you need diffuse of oxygen through the vapor and then oxygen layer to the silicon. So basically, in this process, you're going to make a very thick oxidation layer. Okay, to do that, the silicon vapor heated in a stream of steam or in a wet or dry oxygen nitrogen mixture in high temperature. Okay, and then basically the things that happen is because you're using silicon to become to be silicon dioxide. Okay, with the combination of silicon plus and oxygen. So that means they actually at the end, right? Thickness of the silicon dioxide is proportional, like in this equation. Basically, that means the sum of the silicon actually turn into silicon dioxide. Okay, so that's kind of the magic equation to find out the oxide silicon and then silicon dioxide like density. Okay, and let's keep moving on. So when you grow in that way, the thermally grown silicon dioxide, right? And their properties like this is good insulating layer. So that's useful for the mask, for etching or diffusion, right? So we just explained that you need ion implantation and then you need drive-in diffusion, right? In drive-in diffusion, if you need some protection, right, then silicon thermally grown silicon dioxide is a good layer to protect. Okay, sometimes this is useful for as like a sacrificial layer if you need a certain like air gap at the end, and then you need certain material to be sacrificed at the end. So that's also good for the sacrificial layer. Thermal stresses. Thermally grown silicon dioxide is composed due to the silicon volume mismatch. So basically, silicon dioxide actually deposited on top of the silicon, and their coefficient of thermal expansion is different, right? For silicon is 2.6 times 10 to the minus 6. For silicon dioxide, it's 5 times 10 to the minus 7, right? This is higher. Silicon is higher, right? So basically, if you grow a very thick oxygen layer on top of the silicon, then due to this CT mismatch, actually, when you the summer process done around the 1,000 degrees C, then when it cool down to the room temperature, right? Then this summer CT this mismatch caused the thermal residual stresses. We'll talk about this more later, but this caused the like a bow of the vapor. So we do not grow the oxygen film more than like 1 micron. Right? Otherwise, your vapor is really in trouble. Okay, additive process. So you can in PVD, CVD, we have a vapor deposition method. One is called the PVD, and the other is CVD. So this is like a physical vapor deposition. This is chemical vapor deposition. So this is like a direct line of a side impingement deposition technology. The other one is diffusive convection mass transfer technology. So these are the two. First one is more physical, and second one is the more chemical. Okay, and then PVD we have two thermal evaporation PVD, and sputtering is available. For CVD we have LP CVD and PCVD. Okay, other deposition technology in MEMS we have spin coating or electrochemical deposition. That's the out of scope. This is like if you need a really thick metal layer, but their roughness is really high. So this is like this is not for MEMS, but anyway. So there's two other methods also available. So it's the thermal evaporation, right? This is one of the PVD method, right? So this is like a cold, this is exactly the chamber that I used in when I was in Georgia Tech. This is called thermal evaporator at the time. So basically, what happens is you have target mask here like upside down. So and then you have a molten material located on this here, like this is like if you take a look into it closely, this is like a molten material here to deposit like a aluminum or gold, whatever the like a very pure molten, very pure metal is deposited here. And then what happens is you actually there is a electrode, there is a potential was applied, and then basically you shoot the electron beam into the this solid metal, and then with this energy actually this becomes the molten, and then they generate the metal evaporation. Okay, those metal evaporation was accelerated through the electric field, and then they deposit into the vapor located here, like upside down, right? So that's the way actually you can. That's why you have this is called thermal evaporation. You thermally evaporate the metals and then let them deposit on top of those vapors. Okay, and then it needs a certain vacuum condition, and then depending on process, but the deposition rate between the 50 or 500 nanometer per minute. So this is called the e-beam evaporation or e-beam evaporator. Okay. Sputtering is more bulky metal deposition method. You grow the plasma, and then you have electrode, and then you put your vapor on the cathode. Then basically you have target at an anode, and then you like bombard with positive ion, and then basically then you generate the sputtering of the metal through under the plasma condition. Okay, so for the metals, you using the DC sputtering, but in insulator you have RF sputtering, like the way to generate the plasma is using RF for the insulator. For the metals, you using DC plasma. Okay. So you have choice to metal, like you can deposit for example some metals either by sputtering or by evaporation. So you have choice of two methods. Okay, for insulator you have like RF sputtering is available. Okay, So what is the what is the kind of the way to choose the way to deposit the material? So basically, the better step coverage. Okay, uh, for the better step coverage, basically, let's say you have a step. Okay, let me draw. Let's see. Mm, I'm looking for a way to I can write down for you. Okay, here. So what the better step coverage means, okay, you have like a, this is silicon wafer, and then you have a photo, okay, all right, and then you have a, all right, I need a photoresist protected, okay, then, you want to cover with the metal on top of it. This is a PR, this is silicon, okay, this is a photoresist PR. They are protecting, all right, this protecting around this area. For the good, better step coverage means the metal layer, right, should be when you put the metal, evaporated metal from here, like aluminum, for example, right? Because of their kind of directionality, they are likely going to be deposited on top, right? Like that, not the side of the protected layer, right? Not the side of the protected layer, right? To cover the side wall, right? The sputtering is a much better option than evaporation. So if you have good side step coverage, then sputtering is good. Also, it has better adhesion to the substrate. Sputtering is better adhesion to the substrate. Okay. And then the disadvantage over the evaporation is slower, okay, and then the heating to the secondary. So it is slower, and then there is heating involved in the sputtering. Evaporation is good for the very thin film deposition. Since it doesn't have any good sidewall protection, sidewall coverage by evaporation, sometimes this is good for deposit very thin film by PR. For example, if you want to cover only this part, not the on top of the PR, right? Then when you remove the PR, when you do sputtering, and then the PR, although PR is removed, this sidewall, the material around the sidewall, cause a problem because not clear patterning here. But with the evaporation, because the sidewall protection is coverage is not good, you can, when PR is removed, you can have very clean deposited metal layer on top of the silicon. Okay. All right. Okay. Well, CVD, chemical vapor deposition, is the also I'm not really familiar with this process, but this is using the chemical way to deposit the materials. I'm going to skip it. Sorry about that. LP, well, so there's LP CVD. LP means low pressure. So CVD is done at low pressure. Okay, uh, so this is a good, but the temperature is high, right? I said high temperature is always a problem, but the some material is good for LPCVD. Okay, PCVD, you have a lower substrate temperature, so it's good, less stress, right? Good step coverage. So, but it is contamination is a problem. So PCBD is also available to do that. Okay, surface micro machining. Let's stop at this moment and then let's continue. So I for about 25-30 minute movie clip is necessary to for convenience of upload. I'm sorry about that.